Well, hello again to the Future Internet course. This is the second part of the ML meets or AI meets networking part of the course. So we will have in the last lesson, in the last video, we saw a little bit briefly what is AI and machine learning about, and here we will see some applications of machine learning to different problems in networking. So this will be just a brief overview of what you can do, taking into account machine learning and networking. And then after these theoretical classes done, we're going to go to more practical things. So we're going to work with a first hands-on exercise on machine learning, and then we are going to see some security attacks, cybersecurity attacks detection with machine learning, and some also traffic prediction and classification with machine learning. So in the OSI model, we have, as you know, 7 layers: the physical layer, data link, and network layer that we will call here hardware layers. The transport layer, which is the heart of the model, where you have the TCP and UDP protocols. And then you have the software layers that we call session, presentation, and application layer. As you know, the sender will go down from the application to the physical layer, and the receiver will go up from the physical to the application layer. Okay? And as we also saw in the first part of the course, we have one thing called the control plane and another thing called the data plane. The control plane, we have the control protocols of layer 2 or layer 3, like VLAN, spanning tree in layer 2, or OSPF for routing, BGP for routing, or ARP in layer 3, right? And in the data plane, we just have the MAC address table or the forwarding table in layer 2, and we have the forward information base and the routing table or adjacency table in layer 3, and so on, as the data plane mechanisms. So here we would like to again differentiate between control and data plane. But let's go to network management. So the current situation right now of network management in the real implementation is that despite the progress that has been made by means of machine learning eruption in several fields like computer vision, or actually also speech recognition, even in disease detections and so on, network management and operation is still very complicated, and machine learning has not still been inserted there. It's still in, I would say, its infancy in network management. And because of this network management and operation complexity, network failures are very common. And this is mostly due to human errors in configurations. Therefore, a lot of the community in network management is now working in what they call autonomic networks. And that autonomic networks means that the network management is actually done in an automatic and autonomic way. So trying to avoid as much as possible the human intervention. So what we need is self-configurable, self-remediable, self-optimizing, and self-protecting networks. And this can be done with the help of machine learning. Here I have this is taken from an article that I will pass as a bibliography to you. And they divide the sections in several things that can be done with machine learning. For instance, traffic prediction, traffic classification, traffic routing, congestion control, resource management, and so on and so on. I will show you all of these parts one by one. So traffic prediction or traffic classification, traffic routing, congestion control, resource management, fault management, quality of service and quality of experience management, network security, are the main fields of network management in general. So here we will see how they have been, um, let's say, they have started to work with ML, machine learning techniques, in order to, uh, based on data, try to automate a little bit all these tasks. So traffic prediction is very important. So you know that if we have, as we can see here in the figure, some traffic, and we can predict what is going to come in the future, we can adjust a lot of things or reconfigure a lot of things of our network in advance. If we know that we are going to have peaks of traffic, then we can distribute the routing, for instance, of the network to make it more load balanced. Or if we know that we are going to have actually very few traffic, we can even save energy by turning off some elements of the network, and so on and so on. So it's very important to have the possibility of predicting traffic, and this has been done in networking for a lot of time. So how do you normally do traffic prediction? Traffic prediction implies forecasting of the future traffic behavior in the network. It has been commonly performed using what it is called time series forecasts, or TCFs. But due to the complexity and the amount of traffic in current networks, we have a lot of traffic and a lot of information. Actually, machine learning techniques have been proposed in two cases: traffic prediction as a TSF problem, or as a non-TSF problem. I will show just examples of papers that actually have dealt with these two different problems. You can go more in detail on the papers themselves to see how they actually implemented the technique. So traffic prediction as a TSF problem means that the parameter to consider is the traffic volume. And in this paper of 2006, a neural network is implemented and trained in a predefined path with the following characteristics. So you know the following characteristics of the traffic: maximum, minimum, and average number of bits of the traffic flows. And with that, you know, taking into account the time, the days, the different, let's say, even if it's day or night, and so on. They have predicted the traffic training a neural network in 2006. Traffic classification is also a very important problem of networking. So classifying the traffic, you don't know what is the application, for instance, of the traffic that is actually current and running or traversing your network. It would be very good to, with the behavior of the traffic, know what kind of traffic it is, so I can actually give the traffic a different treatment. So if it is a real-time traffic, I can adjust the quality of service parameters of that traffic to give it a path, for instance, with less congestion or less delay. So traffic classification is essential for telecommunication networks management, as it is needed for the several tasks, but the following ones: capacity planning, security and intrusion detection. If I know what that is, I can classify an attack. This is traffic classification. Quality of service, as I just told you, performance monitoring, and resource allocation. How do you do traffic classification? So traffic classification requires the ability to associate the traffic to something, to predefine classes or characteristics. So I would like to know if my traffic is from some application protocol, like HTTP, FTP, World Wide Web traffic, or peer-to-peer applications like Skype, YouTube, or Netflix, or service classes. The classic way to classify packets has been to use the port number, but the port number is something that maybe you cannot know. You cannot go inside the traffic because it is encrypted, inside the packet itself because maybe it is encrypted. So maybe you should know different things of the traffic in order to classify it. So there has been a lot of work here in traffic classification with ML. This is an example of unsupervised learning clustering in the paper, on this paper of 2006, that is called unexpected means of protocol inference. And classifiers here are trained using a single instance of a protocol that is correlated with the behavior of different protocols. And in this way, you try to, let's say, look at the different patterns to associate to different protocols and have clusters of different protocols taking into account the payload of the packet. Also, this one of supervised learning, it moves the observation point to the network access. So traffic among hosts can be examined. So how many hosts are communicated using which transport protocol. So in this paper of 2010, web traffic over HTTPS can be detected using the features that we can see here. Proximity of web servers to mail servers. So if we have that information, that historical information in the packets. Activity profiles. So mail server users have different daily and weekly behaviors. Sessions duration and periodicity patterns. So with that, we can, let's say, infer if my traffic is web traffic or HTTPS or not, taking into account all these features. And in this way, they had actually a very good precision with the supervised learning algorithm. Here is another example of 2010 called flow-based classification of webmail traffic. So here the classifiers consider a complete communication session. So between one source IP with one destination IP, one source port with one destination port and protocol. And from that, they were able to, using supervised learning, using features like packet size, time between packet arrivals, flow duration, and number of packet per flow, classify webmail traffic. So this is actually, these features are very useful also to classify attacks or cyber attacks as these kind of issues, as you will see when we have the opportunity to make the hands-on lab. Routing. So all of us know what routing is, right? We need to go from one point to the other in a network. So when we are trying to deliver the information from one end to the other, several objectives can be considered, because minimization or maximization of link utilization or quality of service provisioning, and so on and so on. Traditionally, what we do, static shortest path algorithms, as we know, Dijkstra algorithms, Bellman-4 algorithm, Dijkstra algorithm for OSPF, for instance. But what happens if the network is constantly changing, right? So for instance, for routing, actually reinforcement learning has emerged as the main machine learning technique. This is a paper of 2007, but there has been a lot of newer papers in reinforcement learning for routing. Remember that reinforcement learning implements agents to explore the search space, and it learns which is the policy that maximizes a determined reward by means of a trial and error approach. So tries to go through one path, and it has maybe a positive or negative reward, and it tries to then change the path that is traversing the network for the routing in order to trying to maximize the reward. So this paper is based on a Q-learning, which is a type of reinforcement learning technique used to solve the routing problem of one origin and several mobile destinations in a wireless sensor network, in that case, by means of the implementation of an agent that incrementally learns the real cost of the different routes. Okay. So for more information, you can go directly to the paper. Congestion control. This is another very important thing in networks. The congestion control, as you know, is the, let's say, a task in charge of when several packets or when packets are being sent at a rate that is maybe higher than the bandwidth or the capacity of the network, you start to slow a little bit the rate on which you are sending packets, right, to control the congestion in the midpoints of the network. You know that TCP, for instance, has internal mechanisms for congestion control. So it is responsible to limit the amount of packets entering the network depending on its capacity. It ensures network stability, of course, because if I permit all packets coming at very high rate from or entering at very high rate to the network, then congestion will exist and a lot of packets will be discarded. Also guarantees fairness in the resource usage and an acceptable amount of lost packets. So traditionally, TCP congestion control is used for congestion control, and summarizing a lot, what it does is it limits the sending rate at the origin when congestion is detected, right? But using machine learning, also congestion control can be performed in an autonomic and I think more intelligent way. This paper of 2010 shows a machine learning approach to TCP throughput prediction. Using supervised learning, the presence of congestion can be detected actually before you have to drop packets using features like throughput, round trip time, and mobility in mobile networks. And besides congestion detection, another descriptors can be inferred, like packet loss cost. So maybe it's not because of congestion that the packets are being lost. Queuing disciplines behavior, how the queuing disciplines are working in the networking devices, and congestion window updates, among others. So in this way, you can actually, let's say, see how to configure in a best way all the parameters that you need in order to avoid congestion. Resource management and allocation, this is a very important task in networking or in network management in general. So it is the one in charge of network resource controlling, including CPUs, memories, hard disks, switches, routers, bandwidth, access points, radio channels, and frequencies, among others. So depending on the network, is the way to assign resources to the different applications that are demanding them. So when exactly do I have to assign a resource? Where do I have to assign the resource for how long and so on? So how many, for instance, bandwidth should I reserve for this flow? And which will be the path? So I have to configure all the boxes that are in the path, right? So things like that are very important in resource management. So what for? I mean, what do I need resource management? It looks actually for the provisioning of a fixed amount of resources. This with resources I mean bandwidth, CPU, and queue capacity, for instance, in the interfaces and so on. And this should be reserved to satisfy the demand of a service. This is a paramount need for it. This is to predict traffic demand. So if I know traffic demand in advance, I know what do I have to reserve in advance, and then the behavior of my network will be better. To provision in service in a dynamic way is done by means of a good resource management and allocation, so that the network becomes resilient to traffic demand variations. Up to now, what you do in resource allocation or provisioning is just static over provision. So if I need, I don't know, 50 megabits per second for my flow, I say, okay, I am going to try to be safe, so I reserve 100 megabit per second. Okay, and if there is more demand of the flow needs to be reconfigured, another flow actually enter the same path, I have some room for admitting these fluctuations. But resource management can be done in a more smart way, right? So using, for instance, also machine learning. This paper of 2008 is called Quality of Experience Aware Admission Control for Multimedia Applications in IEEE 802.11 wireless networks. So the admission control here for resource management tries to optimize the resources utilization by means of the monitoring and management of each network resource. So example here that is used in the paper, this admission control technique is based on the subjective quality of experience perceived by the users. So a supervised learning technique modifies the following features: codec, bandwidth, delay, and jitter. And we see with historical data of different codecs, bandwidths, delays, and jitters evaluated by humans, providing mean opinion scores, which is a normal metric to measure the quality of experience for each sample. And then with this information, I train a model that will admit or not a new connection request based on the combination of the features that I just mentioned. So if the metric for that new traffic that is coming with this technique is not good, so I will not admit the traffic in the network. Resource allocation with machine learning. So resource allocation is very important. It's a decision problem that tries to distribute the available resources of the network in order to maximize a long-term objective. That can be operator revenue or resource utilization. So to solve this problem, the traffic demand per service should be predicted, right? So for instance, an approach of 2007 also using reinforcement learning allocate several resource types. So for instance, CPU, memory, and bandwidth using fuzzy logic to update a reward function based on the behavior of the search. So with different CPU, memory, and bandwidth, you get a different reward, and in this way you are normally changing the distribution of or the allocation of resources to try always to get the best reward, so to improve the performance of of the allocation. Fault tolerance is another very important thing in networks. What happens if I have a failure in a link or in a node in my network, right? If I have a path from 1 to 5 here, for instance, the red path, but the link from 4 to 5 fails, I need to set up a new path, for instance, 1, 2, 3, 5 here. But this setting up this path should be very fast and should be in order to permit the continuous flow of the information and to avoid disruptions in the network. So in fault tolerance, it has several phases. It includes the detection of the failure, the isolation of the failure, and the correction of the failure. It requires that network operators have a global knowledge of the network, its devices, and the applications that are running all the time should be known by the operators. And current networks are highly dynamic. Now we have mobility, we have 5G or 6G sensors and so on. Therefore, fault tolerance is becoming increasingly complicated. If something fails, it's very difficult now with all the complexity we're managing to overcome the failure. Currently, fault tolerance is reactive. So when I have the failure and then I detect the failure and then I correct the failure or change the path or things like that. And it can be perceived as a cyclic process of detection, localization, and mitigation. However, machine learning mechanisms can provide a proactive approach. Maybe you can even predict if a failure is going to occur, and then you can prepare the network for the failure before it actually happens, and that would be great, right? This is a very old paper, but interesting. It's anomaly detection for diagnosis in fault tolerance, for diagnosis of fault tolerance of failures in a network. And by means of supervised learning, it is possible to learn to distinguish between normal and abnormal network behaviors. And saying, if you see an abnormal network behavior, is because maybe an anomaly of a failure in the network is happening or is going to happen. And then detect this failure and correct the problem between it happens. Let's talk a little bit about quality of service and quality of experience. This is very important. As you can see here, this is like a tube of bandwidth, right? The distribution of the bandwidth in the network when you don't have quality of service rules, you can have video streaming, traffic, general internet traffic, and online gaming traffic. And maybe a general internet traffic is not as important in terms of real-time restrictions as the video streaming ones or the online gaming ones. But if you don't have quality of service applied, then the traffic may be the more in the channel, the one that is going to eat all the traffic can be the general internet use traffic, right? But if you have the rules applied, you can see here that I will give more resources for the video streaming or for the online gaming services. The quality of service and quality of experience compliance determines the success, degradation, or total failure of a service. The service experience in terms of network parameters, for instance, bandwidth, packet loss, rate, and jitter, is called quality of service. So these parameters actually define the quality of service. Quality of experience is an individual and complex measurement that depends on the expectation of the end user. And so normally you have these most tests that I just talked about to measure the quality of experience. And quality of service normally is found by measuring network parameters, right? Bandwidth, packet loss rate, and jitter, and application parameters like, for instance, bit rate. And quality of experience, as I told you, is found normally by means of polls to users trying to find a mean of the opinion score, which normally is called the mean opinion score test. So there is, for instance, 2010, a proposal for quality of experience from users and network perspectives using supervised learning techniques, regression in this case, have been used to quantify the individual and collective impact of quality of service network and application parameters in the user quality of experience. So depending on the different quality of service parameters, what is the impact in the quality of experience? So then I can predict which will be the impact in the quality of experience of the users if I have new network parameters, right, like bandwidth, packet loss, jitter, RTT, video rate, frame rate, and so on. Okay. Let's go to the final one, I think, which is network security. Network security is one of the most important things right now in network management. And economic costs that companies incur due to cybersecurity attacks are huge nowadays. Huge. So every time more and more network security consists of protecting the network from cyber attacks, and it's more and more important every time in current companies or networks in general, because cyber attacks may compromise the availability of the network, and they may also result in non-authorized user access or malicious use of network resources. And this is especially important in critical infrastructure on cyber physical systems, like, for instance, in the energy systems. If I attack the communication network of the energy system, I can, just put the system in an unavailable state, right? So no energy for, I don't know, a city or as part of a city. So it's very important to have good network security techniques installed to protect against cyber attacks. So actually, machine learning can be used to several things in cybersecurity. In cybersecurity, machine learning has been used a lot of time ago. You can see papers here from 2003, and this is actually being implemented nowadays in networks in general. So intrusion detection, for instance, due to traditional attacks, can be detected with supervised learning techniques. We will see in the hands-on exercise something like that. Something like this is very, very, very used currently. Intrusion detection due to anomalies can be detected with unsupervised learning techniques. So new patterns that you don't know are not labeled, but you can detect using unsupervised learning techniques. And intrusion detection using reinforcement learning is also being studied. So you can see here 3 papers with these 3 different techniques. If you want to, let's say, dig into the details of these papers, they are going to be given to you in the course, so you can search for them. So this was actually what I wanted to tell you about the intersection of machine learning and networking, and how this is important nowadays, as you can see, that can be applied in several tasks, important tasks of network management. So this was everything for this video. And remember that we are going to do some hands-on and lab activities with machine learning and in its intersection with networking. Thank you very much.